Welcome to an introduction to graphs. A graph is a relation from a set S to itself. For an example, consider the set S. It contains five elements A, B, C, D and E. So the set S is equal to set A, B, C, D and E. A relation from S to S is a subset of S cross S, that you know. Any relation from S to S is a subset of S cross S. That's written are the relation defined from S to S, and such a relation is given here as an example. We can consider this relation, and since any relation is a subset of S cross S, we have ordered pairs of elements in that relation. Here we consider the ordered pair A, A, B, A, C, B, C, B, E and D, E. We can represent this relation using a picture, using a graph, and that graph is written here. Let's see how this graph is drawn. I will explain that. Here, first of all, we put 5 dots on the plane. Those dots are then labeled with the elements which are present in the set S. So we give the labels A, B, C, D and E to the 5 dots that we marked on the plane. After that, we consider that relation, and the pairs of elements present in the relation is considered one by one. First element is A, then in the figure we draw a line starting from A and ending at A. And since AB the pair AB is present, so we draw a line from A to B. Since AC is present, we draw a line from A to C. And BC is present in the relation, we draw a line from B to C. In a similar way we draw lines from B to E because B is present, and from D to E, that relation is also marked there in the graph. And this is the way we construct that graph, that figure. And this kind of figures are called graphs. So we can say that a graph contains some vertices, also some dots. This graph contains dots and some lines connecting these dots. Some of the lines connecting these dots. Of course, there are missing connections. You can see it was possible to include a line, an edge from D to C. Here in our language, in the language of graph theory, the words line, edge, etc. are synonyms. Also, the vertices, the words vertices, node, vertices, node, nodes, points, all these are synonyms. Okay, and in this graph, there are 5 vertices marked, or 5 points marked. Connecting these, connecting some of the pairs of these vertices, some edges are included. Edges or lines are drawn. This way we obtain this figure, and this kind of figures are in general called graphs in graph theory. So we can say that considering a set, then defining a relation from that set to the same set, after drawing pictorially that, after representing pictorially that relation, we have obtained a graph. I would like to add one important thing, that this way is standardized. This method can be used always to draw a graph. I mean, starting from a set, considering a relation, we can draw a graph. But as we go further, we are going to see some different forms of definition, some slightly different definition for graphs. Some mathematical, some descriptive definitions are available that contains that uses the notion of sets. But this method that we have seen, the method of defining a graph that we have seen using the relation, is also very useful, and I would like to say that it is basic. Next, see in the figure, the elements of the sets are denoted by, okay, and these points we discussed. In the previous figure, the elements of the set are denoted by dots, and the relations are denoted by edges or lines. Dots are also called vertices or points. We can call the figure a graph. The set of points in the graph, the set of points, so we consider the set of points in the graph, we will represent it by V of G, where G is the letter used to represent the graph, that figure. Then the vertex set of we have a set of vertices. The vertex set of that graph will be represented by V of G. And we also know that there is another related set that contains the edges or lines, and that set will be represented by E of G, EG. So here we have, in the set form, we have V of G is equal to set A, B, C, D and E, and E of G is equal to the pairs AA, AB, AC, BC, BE and DE. Now we are going to see the formal definition of graphs, and this definition is available. You can see this kind of definition in every graph theory book, in the first section of the graph theory book of any graph theory book, because without this definition nobody can study graphs and graph theory. And this is the standardized definition. It's the standard definition for graph theory, but the previous definition I used was not standard, and you cannot see that definition in all books, but in very rare, in some of the rare books you can see that definition. But that's the basic idea behind the graph. Actually, that's the basic idea behind the graph, because every graph tells us about some relation that exists among the members of members of that members of a set, that exists, the relation that exists among the members of a given set. Here, see, the given set is S in our previous example. Okay. A graph G equal to VE. We are going to represent the graph using this notation, G equal to VE, where V is the vertex set and E is the edge set. It consists of two sets V is the first set is V and the second set is E. First set is the set of vertices and the second set is the set of unordered pairs of elements of V. See it, look at this statement. The second set is the set of edges, okay, but it is the set of the unordered pairs of elements of V. If you have two sets, we can make two types of pairs. One is ordered pairs and the other is unordered pair. What's an ordered pair? See, if A and B are two elements of a set, see, consider this set. If you consider this set A and B here, you can see A and B are two elements. Now, using these two elements, you can make an ordered pair AB. In such cases, if somebody write BA, that will be different from AB in the case of ordered pair, because the order of the elements present in that pair is very important. We treat the order differently. In the case of AB, what was the order? A first, then B second, B then second, and in the case of BA, B comes first and A is the second element. So since the order is important, we treat these two arrangements different. But in the case of unordered pairs, we treat AB and BA equal, because order of the element is not at all important. Now coming back to our point last discussed, okay, the pair of elements. This is the formal definition of graph, the formal definition of a graph that you can use anywhere. You can use everywhere, and this is more acceptable. And after defining it, we need some examples to get more understanding about that concept. We present some examples here. Example 2. Here, this one is the first example of a graph, but in the order of the examples present that here in this material, it comes as the second example. In this figure, you can see that some dots are here. It also contains some dots. The dots are labeled A, B, C, D, and E. And edges are also present in the figure, but you can see the edges are also labeled. Those edges are labeled here. You can here the first edge E1. First edge is labeled E1, and that connects A and B. E2 connects B and C. E3 connects B and C. See, that's a different type of connection, because both are same actually. E1 connects B and C. E2 connects B and C. Similarly, E3 also connects B and C. So these two edges or lines behave alike. They are same, and this kind of lines are called multiple edges in the language of graph theory. This kind of edges are called multiple edges. So what is a multiple edge? Multiple edge is an edge. Multiple edge is an edge. Multiple edges are edges those edges having same end vertices. Here, see, the end vertices are B and C. Since these two lines are the same end vertices, these lines are called multiple edges. But this kind of edge, there is another edge. You can see E8 is an edge, and that starts and ends at the same vertex. That originates and ends at the same vertex, and so this edge is called a loop, it's called a loop in graph theory. A loop or self loop. And the other edges, thinking about other edges, you can say that E4 links C and D, E5 connects B and D, E7 connects E and D, E6 connects B and E, etc. And this graph will be called G1. G1 is the name given to this graph. So you can now write, after analyzing that picture, each component of studying each part of that graph, studying each point of that graph, you can now write the vertex set of the graph V of G1. Vertex set of G1 is V of G1, and that contains elements A, B, C, D, and E. And the edge set of G1, E of G1, is here. We are using the labels given, the straight labels given in the figure can be written here: E1, E2, E3, E4, E5, E6, E7, and E8. Of course, behind these labels, related to these labels, E1 we have pairs. E1 we have pairs of vertices. You can write, you can replace E1 by AB. You can write E1 by AB. You can write E2 by BC. You can write E3 by BC, etc. You can replace. So by replacing these labels of edges, you can include suitable pairs of vertices. Okay, that way also you can write that edge set. Thus we have the vertex set and the edge set related to that graph. The edges can also be written as unordered pairs. Okay, and that's done here. That is written here. The unordered pairs used. Unordered pairs of vertices used in that graph can be used to write the edges. Now coming to the third example. Here the second example of the graph. In this graph, and the graph is called G2. In this graph, how many vertices are there? One. First, you should count the vertices, or you should take note of. You should note the number of vertices. 1, 2, 3, 4, 5. 5 vertices are there in the graph. And these vertices, the labels given to the vertices are different. 1, 2, the number labeling is used here. We label the vertices using numbers 1, 2, 3, 4, 5. So the vertex set of G2 is 1, 2, 3, set 1, 2, 3, 4, 5. But the edge set here in the graph, the edge set are E1, E2, E3, E4, E5, and E6. These edges are now you can write them either using that labels or using the ordered it's unordered pair, using the unordered pairs of vertices, and that is written, that is used here. But first that is written, that's 1, 2, 2, 3, 3, 3, 3, 4, etc. Looking at the figure, you can identify the vertices that come as the end points or end vertices of the edges, and then using them you can write this set. And this is another representation. This way also you can write the edge set of the second graph G2. Now we come to the second section of the first chapter, 1.2, section 1.2. Here it gets it is given the title. That section gets the title graphs as models. Some previous videos I have explained about the use of graphs as models in the real life problems. For representing the problems or problem elements, we can use graphs or graph theoretic methods, and we can use the advantage of that kind of representation is that we can use the methods, established methods or techniques of solving problems to solve the problems in real life. So that is the advantage. So thinking about having some these ideas in our mind, we are going to see some examples of such problems that are very famous in the literature of graph theory. First problem is the connectivity problem. It's called the connectivity problem. First problem. In every case, the problem will be described in the first part, and after that, we give a mathematical, more correctly, a graph theoretical representation. A graph theoretical representation of the problem, and then in most of the cases we give some hints about the solution, or we give some hints about the importance of that problem. Actually, some problems demand a very deep and wide study, and it will take hours of serious study. So we accept these problems just to get some basic understanding about the applications of graph theoretic techniques in solving problems. This problem is associated with a network of telephone lines and poles. This is the background of this first sentence. He tells us about the background of the problem. This problem is associated with a network of telephone lines and poles. We want to find the network's vulnerability. In the word, you can see here the Y, the last letter is Y, that's missing. Vulnerability. So we want to find the network's vulnerability. What is the network? Network is the graph behind. There will be a graph behind that problem, or representing that problem. That will be called the network. That is called the network. Find the network's vulnerability to accidental disruption. Or we want to identify those lines and poles that must stay in service to avoid. We want to identify those lines and poles. Those lines and poles that must stay in service. That must stay in service in order to avoid the connectivity. In order to avoid disconnection of the network. Disconnecting of the network, not connectivity. This is the disconnecting of the network. If we have a network to discuss, and if some nodes or edges are removed, then some networks will get disconnected. A network which is connected is more useful and more meaningful than a graph which is disconnected. In some cases it is like that. So connected graphs are very important and useful. So we are much worried about the disconnection of the network. What is the point? We are worried about the disconnection of the network, disconnection of the graph. When it will get disconnected. When the connections in the network will be lost, and due to what changes taking place in the graph, that disconnection will take place. Like that. These are very serious questions that graph theorists face and try to find answer. While studying connectivity type problems. So in this case, this is the problem, and this is the basic main question, and those lines and poles that must stay in service to avoid the disconnection, or avoid disconnecting the network. So for supporting this the above statements, we have an example network. See, suppose this network, and this network in that sense, in the sense of that problem, we call it a network, but it's a graph, that, because it satisfies all the properties of a graph. What are the properties of a graph? The properties of a graph are mainly it must contain some vertices. some set of vertices, a set of vertices must be there. You can see in this graph there are this one A, B, C, D, E, and F are the vertices. And then we look for edges. Yeah, the edges are also present in this figure. Those edges are T1, T2, T3, T4, T5. These are the edges up to T8. 8 edges are there in the graph. So we can call it. We can call this figure a graph. You can write the vertex set and edge set of this graph. But in this problem, now for the time being, we will call this a network. And in this network, if we select this vertex, suppose we take this vertex. The vertex that vertex is D, labeled. The vertex labeled as D. You just think about removing that vertex. What happens if we remove that vertex? If we remove the vertex, naturally there are edges linked to it. You can see in the figure, you can see there are 4 edges which are linked to it. Naturally, those edges will also go from that figure, because you cannot keep those edges in the figure even after removing that vertex, because after removing the vertex you cannot keep that edges, because these edges have no existence without this vertex. That is because of the fact that every edge has 2 end vertices. So by removal of the vertex D, by removal of the vertex D, we are removing one of the end vertex of the edge T6, T4, T5 and T7. As a result, that edge will also have no meaning. So along with that removed vertex D, the edges T5, T4, T5, T7 and T6 will also disappear. What happens then? You can see that the graph then breaks into, the network breaks into two connected networks, small networks. What are those small networks? You can see here this part, on the left hand side you can see that it is ABC. That network reduces to a triangle, and on the right side, on this side you can see that that network reduces to just an edge. And as a result we get 2 small networks. That means the connected network has broken into 2. So this vertex is very important in this network. It's an important guy in this network. So be careful while removing this vertex, because that will affect, the removal of that vertex will affect the whole existence of the network. But see, on the other hand, if you try to remove this vertex, the vertex B, what happens? Now, no, nothing serious will happen, because that remaining network will, something happens, because associated with that vertex V, that just T1, T3 and T4 are there, so that edge will also disappear. So that will affect the structure of the network. That removal of the vertex B will affect the structure of the network. But another thing is that the network is not disconnected. It is connected. So and similar thing happens when we remove C, the vertex C, or the vertex A, or the vertex C and F. So those vertices are not much important, not as much important as the vertex D, because it's an important guy. That can cause, the removal of that vertex can cause the whole network disconnected. Okay, and in a similar way you can study the removal of edges from the same graph. See, suppose you remove the edge T6 if you remove the edge T6, what happens? Only that edge will go. The remaining or its two end vertices will still be there in that in the graph. It will remain in the graph. I mean, the vertices D and E, and these are the end vertices of the edge T6. It will remain in the graph. It will not go. Similarly, suppose we remove T8. If we remove T8, then the vertices E and F will remain in the graph. So you can try the removal of more edges. You can try the removal of more and more edges. As by you can see by removal of a single edge cannot affect the connectivity of the network. The network can continue to be connected even after removing say a single edge. But suppose we remove one more edge after removal of an edge. For example, consider T6 is first removed, and we then remove T7 also. Or simultaneously, suppose we remove T6 and T7. Suppose we remove T6 and T7 simultaneously. What happens to the network? Then the network becomes disconnected. Another example, as an example you can consider, suppose we remove T6 and T8. If we remove T6 and T8, then also the network becomes disconnected. But if we remove T4 and T3, the two edges, that network, then the network will still be, it will continue to be connected. It cannot be disconnected. For making the disconnection, you have to remove three edges simultaneously. So by changing the position of the edges among the whole edges present in the graph, you can see that you can draw an idea that the disconnection of the graph can cause due to the removal of edges, but that depends on the position of the edges and the number of edges actually removed from the network. So what are the factors affecting the this connectivity of a network while removing edges? The position of the edges and that number of edges actually removed. All these can affect the connectivity or disconnection of the graph. Now the question is how many, and continuing that the remaining part of the same problem. The question is how many lines, and so in this part I have explained many of the ideas that we are going to see here in this writing. So I will go just by reading those lines. The question is how many lines need be removed to make the graph disconnected. Removal of one line cannot make the graph disconnected, but the removal of either T7 and T8 or T7 and T6 or T6 and T8 can make the graph disconnected. But when we consider the vertices, the case of vertices, the removal of a single vertex D can make the graph disconnected. These ideas I explain it in much detail, in more and more details. Now we can now come to the second problem. That second problem it is given in that material in the chapter. It can be called the matching problem. It is famous as matching problem. Matching problem, it's an interesting problem. It has many versions. These all of these problems are very summary. It's a summary of a very large, very big problem in that require very deep study. So I have mentioned that sometimes early. Now in the matching problem here, you can see here this problem is described here. as a very small problem. Now we have 5 jobs and we have 5 jobs and 5 people, and the problem explains about jobs and people. We have 5 jobs and 5 people. We denote the jobs by letter A, B, C, D, and E. The jobs are denoted by A, B, C, and A, B, C, D, and E, and okay. An error has occurred here. The first representation is that of people. We have people and jobs. The people are denoted by A, B, C, D, and E. It's a mistake. This part should be corrected. This should be corrected as people. Okay. The people. There are 5 people. The people are represented by the letters A, B, C, D, and E, and the jobs are denoted by small letter A, B, C, D, and E, small letters. And we have the following list of jobs. Along with this, we are given a list of the list of jobs that can be performed by the people. Every people cannot perform all jobs equally. A particular person A can he knows to do only 2 jobs, and those jobs are C and D. So A can perform the jobs C and D, and B can perform only one job, that's C can perform the person C can perform the jobs A, B, and E. D can perform the jobs C and D, and D and E can perform the jobs B and E. Now the question is whether we can find a perfect assignment of jobs to people. We want to assign jobs to people. What's a perfect assignment? A perfect assignment of jobs means you take a person, he must get one job that he prefers or that he likes, that he knows to perform. So you can consider this list as preference, or you can treat it as preference, or to treat it as his ability to a person's ability to do the job. In various ways you can treat this list. Okay, whatever is that kind of treatment you can, the method, the problem can be solved in the same way. So the answer to this question, we are asking a question. In the problem is basically based on a question. That question is, can we find a job? Can we find a job that can be assigned to each and every person? If there exists such an assignment, so the question is, can we find a job from the list of jobs? Can we, you can assign only C to either C or D to A. In the case of, as we come to the case of the first person A, you cannot assign that the job E to that person A, because that job is not there in the list of in the preferred list of A. The person A can do only the job either C or D. So you cannot assign E to that person. Therefore, this is the preferred list of the jobs to that person. So you can either assign C to A or D to A. But one more thing is that once you assign C to A, it cannot be assigned to another person. It cannot be assigned to B. Otherwise, the answer to the problem could be obtained easily, because you can simply assign C to A and C to B. Then what will happen? The people, 2 people are assigned to one job, and then they have to do the job half portion each. First part or half of the job can be done by the first person, and only half of the other half should be done by the second person. It's a waste of money, everything. It's a sheer waste. So it should be, that situation should be avoided. It is not economical. So avoiding such situation, a particular job can be assigned to only a particular person, Not only that, a job can be assigned to a preferred person, or that if the job that job must be preferred by a particular selected person, and these are the conditions that should be followed when we find an answer to this problem. Okay, that way if we think, you can assign the job A to either any one of the job A, B and E, A, B and E to the person C. But if you assign B to C, then that job cannot be assigned to anybody else. So it cannot be assigned to E. And finally, the question is whether there exists a complete and perfect matching for this list of persons and jobs. Does there exist a matching? A matching, a perfect matching means every person gets a job from his list of jobs. But in the case of this problem, the answer is no. A small description or a small reason for that no answer. The answer is no. Answer to that question in this case, in this problem, is no. A reason is also can be given. Why? Because you consider the combined list of three persons. See, three persons. Those three persons, the persons are A, B and D. Here for that, to explain the reason for that, we take three persons A, B and D, and we look at the combined list of the three persons. The combined list is CD and C here. So CD itself, CD, C and CD, again CD. So the combined list contains only two jobs. We have taken three persons, and their combined list, their preferred list contains only two jobs. It's a problem, because after taking three persons, how many jobs must be there in their combined list? There must be at least three different jobs. There must be at least three different jobs. That's not it is not that situation in this case, because there are three persons taken, A, C and D. A, B and D. A, B and D are the three persons taken. In their combined list of jobs, we have only two jobs, preferred jobs. So you can, if you try, suppose you try to assign C to A and you assign D to D, this D to D, then you need one more job to assign it to B. But there is no such job left, because in the list, how many jobs are there in the list? In the list there are only two jobs. So the problem there arises. As a result, at this moment, it comes to an end. The problem comes to an end, and you should stop that. You should stop your attempt to find the answer with the conclusion that there is no such a perfect matching. There is no such matching for this assignment problem. It's an assignment problem, matching. So matching kind of assignment problem. This problem can be called assignment problem also, another name. Okay. And you can see that reason also. The question is whether we can find a perfect assignment of jobs to the people. How can we do this? Okay. And this problem can be, the most important thing that I didn't explain, that I am coming to that part. You can represent the situation using a graph. The graph theoretic representation for this problem is shown here. What is done here? How this graph is drawn? You can see the vertices A, B, C, D, and E. The vertices, the persons A, B, C, D, and E are represented in the figure by dots. 5 dots, and on the other side you can see the jobs A, B, C, D and E. These are the jobs. These jobs, 5 jobs, are represented by other set of 5 vertices. And some you can also see a collection of edges connecting the first set of vertices to the second set of vertices. Of course, these connections are these lines are drawn looking at the list. You can come back to the list. See, the first part of the list, A is assigned to C and D. Then come to that graph, come to the picture. You can see a line is drawn from A to C and A to D. Similarly, since B has a C in this list, we draw an edge from B to C, and that way you can see that all other lines are also drawn in the same way, following exactly the same rule. That's all. Then looking at the list, see here E. The person E has D and E in his list, so edges must be drawn from E to B and E to E, E to B and E to E. The edges are drawn from E to B and E to E. Okay, the answer to the problem is given here, and the answer to the question whether there exists a perfect matching of the jobs to the above problem is no, because the combined job list of the people A, B and D contains only 2 jobs, and that is those jobs are C and D. We cannot assign 2 jobs to 3 people, subject to the condition that only 1 job is assigned to 1 person. Okay. Now, and the third problem, it is famous as traveling salesman problem. The traveling salesman problem. What's it? A salesman's territory. A salesman territory include several cities. A salesman's territory include several cities with highways connecting certain pairs of cities. And this salesman wants to find a route. The salesman wants to find. This is the problem part. This is the description, and this is the condition part. First part is the condition part, and this is the problem part. The salesman wants to find a route starting from a city and passing through each city. Starting from a city, he must start from a city of his choice. Which city he likes, that city he can choose. He can choose that city, and from that city he could travel. He could choose a highway path to reach the next city, and from there he could reach another city, and he can continue. Likewise, he can continue up to covering all the cities. He must be able to cover all the cities in his territory, and finally he must be able to come back to the starting city. That is the most important. But also in between we should note that in between this travel, not one important thing, that the cities should not be repeated more than one time. That is, the city must come in that travel exactly one, or each city must be visited exactly once. And these are the problem part, along with the condition. Okay. Next you can see 2 figures, 2 graphs. 2 graphs you can see. In the first figure you can see the graph G1, and the second figure you can see graph G2. By examining the 2 graphs, you can see that there are differences in these graphs. What are the differences? Of course, and here similarities also there. are also similarities are also there. What are the similarities? 1, 2, 3, 4, and 5. There are 5 vertices in the graph. Here also 1, 2, 3, 4, and 5 vertices are there. Number of vertices are same, but what about number of edges? 1, 2, 3, 4, 5, 6, and 7 edges. 1, 2, 3, 4. 3 plus 3, 6 plus 1, 7 edges are there. Here also 1, 2, 3, 4, 5, 6. 4, 5, 6, 7. Then both graphs contain 7 equal number of edges, 7 edges. But these are the similarities. But beyond that, there exists there are dissimilarities also. There are differences also. That for finding that difference, you must closely examine. You should do more comparisons between these two graphs. That main part of difference is that here the connection between these two vertices. See here connecting to two diagonal vertices, you can for convenience you can call these two vertices diagonal, and these two diagonal vertices are connected by edges through a vertex. Here also that happens, but you know an edge is there from the middle vertex, from this vertex, from the vertex 3 to the vertex 1 there is an edge, but that edge is missing here in the next graph, in the graph G2. Instead we can see a new edge is there, and that connects these diagonal vertices, these two end vertices directly using that edge. Okay, and that is the difference. So this makes some difference, and you are going to see what is the importance of these two graphs in the current problem. You know, you can try starting from a vertex, from any vertex of this graph, without taking your ruler or pencil or your pen. Without taking your pen, you can try to trace the edges along the. You can try to trace the edges in the graph and try to get back to the starting vertex. But in between this travel, you must visit each vertex exactly one. But you can see that it is not possible to attain such it is not possible to complete such a travel in the first graph. But in the case of the second graph, you can see that such a travel is possible. You know, you can start. I can demonstrate one. You can start at this vertex and you can come to this vertex, and then you can reach the vertex of 5. See, that is from starting from 1 you can reach 3, and you can reach 5, and then you can reach 2, and then to reach 1. From there you can reach you can come to 4, and then 5 you can come to 5. Then again you can go this way. You can take the path, you can take the edge G, and you can come back to 1. In a similar way, you can start I think you can start at any vertex and you can complete this this travel, but excluding one vertex. See, take this example. That also is possible. That also possible. If you try from here, from the vertex 3, you can take this path, and okay. Suppose you take this path and reach here 1, then reach here 4, and then 5, and suppose you take by chance you take the path from the edge E to reach 3, then your travel ends there. By tracing only a triangle, which is only a part of that graph, without tracing the other remaining edges, you have to end the travel at the vertex at the starting vertex 3. So that's a problem. So you must be a little bit conscious about you should be careful about the starting vertex. So that's very important. I mean, you cannot start at any vertex and complete that kind of travel and reach back to the starting vertex. So that's a problem. But beyond that problem, you can if you can overcome that by selecting some after thinking, by selecting, if you apply thinking, some kind of thinking, and if you select a starting vertex, then you can of course you can complete the travel perfectly in the second graph. But it is not possible wherever you start in the at a vertex in the first graph. It is not possible to complete such a travel in the first graph. That is the problem with that is the main difference between these two graphs. So and that is described here. You can see what I have explained is written here in words and sentences, and okay, you can go through and I will quickly read it. The graph G1, in the graph G1 there does not exist any closed path satisfying the condition, but condition, what is the condition? Condition explained in the problem. And but in the case of graph G2 there exists a closed path, there exists a closed path in the second case, a closed path that is 1 9 2 D, and this is that closed path. See, sorry, 1A, it is not 9, it's 1A 2D 2D 5 3 5 3 then B1, etc. And this is that closed path is the chain of vertices and edges starting at 1 and ending at the same vertex. Now the problem 4, coming to the problem 4, it is the planarity problem, and we have three houses. We have three houses. And we have to supply with these houses with the electricity. Three facilities are there: electricity, gas, and water facility. So we have to supply electricity, gas, and water to the three houses, and these facilities are provided using pipelines. Can we lay pipelines to the above three houses from the supply sendays? There are supply sendays also, and from these supply sendays pipelines are laid to the houses. But this pipeline, the question is that can we lay the pipelines avoiding the crossing of the pipelines? See, that problem can be represented by dots and lines suitably drawn. Here houses are represented by vertices, and facility sendays are the facility sendays, electricity facility and gas facility and water facility sendays are denoted by suitable vertices, three vertices, and then the lines here represents the pipe connections, and the pipe laid between the electricity facility center to the first house is drawn here, and G from the gas to the first house, etc. All the lines are there. You can see all these pipelines are drawn, are laid there. And the problem now, I shall repeat that problem. Can we lay the pipelines? Here you can see the crossings there are so many crossings, and by avoiding the crossings, is it possible to lay the pipelines? That is the question. But you know, here in this case, in this case, you cannot redraw the pipelines, or you cannot relay the pipelines avoiding the crossings. That is the answer. But for explaining it further, you need more ideas that is going to study in your in your future classes. So I am not going to get into the details of that solution. Now coming to the fifth problem, the coloring problem. We have the coloring problem. Coloring problem is like 6 radio broadcast. That problem goes reads like 6 radio broadcasting companies are there. C1, C2 and C6 are the broadcasting companies, and they have applied to the Minister of Broadcasting for frequency channels. If the transmitters of two companies are within 200 kilometer of each other, if they are within 200 kilometer of each other, and they cannot be assigned the same frequency, frequency sender, there will be okay, they cannot be given the same frequency, and there will be too much interferences. Because there will be too much interferences if we give same frequencies, and then we assign as small as we assign as small as the number of different frequencies. We assign as small as the number of frequencies as possible, taking the interference into account. We have to assign the frequencies as small as possible, taking into account the interference. As an example, consider to explain it in detail, and we have an example. We take an example. Then consider the graph G given below. It contains the vertices C1 to C6 and two vertices CA and CJ. In the graph, two vertices CA and CJ are joined by an edge if and only if two companies CA and CJ have their transmitters less than 200 km apart. If the transmitters are less than 200 km apart, then only those two points are joined by a line. And suppose we assign different colors to the vertices of G in such a way that no two vertices of the same colors, no two vertices of the graph get the same colors. Vertices of same colors are joined by an edge. No two vertices of the same colors are joined by an edge. We can then think of the colors as representing the frequency channel, and we want to avoid the minimum number of we want to find the minimum number of colors that are required to color the graph. And this is the graph representing the problem, and here you can see edges are there. These C6 and C2 are linked by an edge because the frequency is frequencies are the transmitters, the distance between the transmitters are at least 200 km apart. If they are less than 200 km, at a distance of less than 200 km, then that frequency issue takes place. Interference of frequency take place, and this way you can convert it into a coloring problem. Coloring problem is also a wide area in graph theory, and so that need a much more deep attention and serious study. Now, problem 6. Coming to the problem 6, a company has beaches in each of the cities. Benches in each of the cities, in each of the cities C1, C2, etc. to C6, and then the airfare for a direct flight, direct flight from the city CI to CJ. From CA to CJ is given using the weight, given by the weight ijth, the ijth element of the following matrix. Yes, it is given as the weight or as a number in the matrix form. It is given. The company has benches, benches, or it's anyway anything. A company has you can read it as some offices. The company has offices in different cities, etc. Likewise, it can be changed. Now, in 6 different cities, and also officials required to travel from one office to another office using air travel facility. So this fare is important in this problem. The fare of travel, direct air travel from one city to another city, from the ith city to the jth city is important. You can see this is the matrix showing that travel fare from this city. These are the cities C1, C2, C3, C4, etc. 6 columns, 6 rows, and 6 columns represent also represent the cities, 6 cities. And from the first city to first city there is no travel because the same city, so 0 is the air travel. But from the first city C1 to the second city, travel of fare of the travel is 50. And if there is no air connection, the flight connection between two cities, here you can see from C1 to C3, from C1 to C3 there is no air connection at all. So the travel cost will be here included as will be considered here as infinity. So that is the way. This is the way we fill up that that matrix. After that, the company is interested. What is their interest? The company is interested in computing a table of cheapest fare between pairs of cities. They want to construct a table of cheapest fares. Everybody, maybe company or a person, everybody is interested in a cheap rate. So they will try to. They are trying to find a table of cheapest rate. Even if there is a direct flight between two cities, this may not be the cheapest route. That can happen. Even if there exists a direct flight from one city to another city, that may not offer the cheapest route. Maybe some other route, some diverted route, so more lengthy route may offer a cheapest the cheapest rate between two cities. Now we can first represent the situation by a weighted graph, and that is a graph with weights attached to the edges according to the airfares as in the figure below. See, you can see here a graph is drawn. In this graph, vertices stands for what? Vertices stands for cities. Vertices stands for cities where the company has offices, and the weight, you can see the edges are drawn. The edges stands for direct flights. The availability of direct flights between two cities, between C1 and C5, there exists direct flight is available, but between C5 and C2 there is no direct flight, so no edge is included. No edge is included. So along with these edges you can see the values 10, 50, 15, 20, 40. These are the values that stands for the cost of direct flight. Cost of what are they? They are the cost of the charge of the direct flight. Now the problem can then be solved using the Dijkstra's algorithm. Yes, it's another important topic. Dijkstra's algorithm. We need more time and more previous preliminary work to explain that. So that is left for another occasion. Yes, and this type of problem is called the shortest path problem. You should remember mainly that point. Okay, thank you for listening.